Are we going?
Yep.
Aloha! Welcome to another exciting edition of Physics 251 Lab. Today we're going to be doing torque. We're going to mess with this simple system. It's basically like a seesaw. I'm going to do an example that shows you how we can use this simple system as a, we can use it as a balance. That is, we can measure the mass of things. Here's one of the blocks that we had from the midterm. If you remember, the mass of the block to two significant figures was 260 grams. And so I'm going to try to use this system to measure that. So if you kind of look right here, so this is the fulcrum of our seesaw. It's just a board, so it's not going to be 100%. There'll be a little error involved, a little margin of uncertainty. But you want to check and make sure that your meter stick balances when it's at the 50 centimeter mark. If it doesn't, you can tack on a little paper clip on one side to balance it. This one's pretty good. And so what I'm going to do is I'm going to take this guy and I'm going to get him so that he's centered about the 80. So right about here, he's centered at the 80 centimeter mark. And then I'm going to set him up on here, centered at the 80 centimeter mark. And I'm going to check and make sure that he's centered. So it should be something like this. 84.76. Okay. So he's centered. You notice I put this guy here to balance it. Okay, so he's at the 80. And then I'm going to put masses at 10 to try to balance this guy. Okay, so I'm going to put him at the 10 centimeter mark. You notice I put the little slit right here so that I can make sure that it's exactly centered at the 10 centimeter mark. It's important where it's at. So 100 doesn't quite balance it. I set a 50 on here. It's not quite balanced. I can tell when it's going to start to balance. This end will lift up a little bit. So let's try 20 on here. So I stick a 20 right there. Still not balanced. I'll try 10. Oops. You're getting close. So what do we got now? We got 150, 170. I'm not sure. We'll count it at the end. So I put another 10 on there. And there we have it. So now it's balanced. Right, because this guy comes up, so I can pretty much do that. And so that balances it. Let's see here, that's 150, 70, so it's 190 grams. So let's, so I'm going to draw the free body diagram of that guy. And so over here is the 10 centimeter mark. At the 10 centimeter mark, I have this force. It's the weight of, I'll just write it this way. It's 0.190 kilograms times G. Right? It's the weight of the 190 grams times gravity. Here at the 50 centimeter mark, if you look at that guy real quick, the 50 centimeter mark, there's actually a couple forces that act there. There's the weight of the meter stick itself, and then also the board presses up at that spot. So we'll have, so we'll call it weight meter stick, and I'll call it FNB, the normal force of the board that it's resting on. And at the 80 centimeter mark is the weight of, I'll call it M, since I used mg over there. I'll call it the mass of the little board times g. Okay. So the trick is we can figure out what this mass is by using the sum of the torques is equal to 0. Because the sum of the torques has to be equal to 0 when that guy is balanced. Okay. As always, when you do the sum of the torques, you have to choose your axis of rotation. So I'm going to choose the axis of rotation. The smart place to choose is that place, because you got this forced normal board which you don't know and you don't really care about. Okay, so if that's the axis of rotation, there's only two torques. The torque due to this guy, which happens to be a counterclockwise torque, and the torque due to this guy, which is a clockwise torque. Okay? And so I like to write this equation, sum of the torques is equal to 0, as the torque counterclockwise will be equal to the torque clockwise. The torque counterclockwise comes from, so now we'll put in the equation for the torque is RF sine theta, and we'll put that in for the counterclockwise guy is the 190 grams on the left, so we get 0.190, oops, my bad. Let's put the R in first. The R turns out to be, the definition of the R is the distance from the axis of rotation to the point where the force acts. So in this case it's 40 centimeters. We can write it as 40 centimeters. Normally I like to use meters, but I'll show you why it doesn't matter here. So we got 40 centimeters. Then the force is the 0.190 kilograms times G, and the sine, the angle for that guy is 90 degrees. Okay. I'm gonna need the board strength here. Okay, so that's equal to the other torque, which is the clockwise torque, which comes from this guy, and the R for that one is going to be 30 centimeters. Get Katrina on the camera there. 30 centimeters times the mass of the board times G, and the angle for that guy is also 90 degrees. Sine of 90 is 1, you get rid of that. The G's go away. Okay, so you're left with, if you solve for the mass of the board is equal to 40 centimeters times 0.190 kilograms divided by 30 centimeters. Okay. If I get out my trusty calculator, give me 1 second. So we get, so you see why it didn't matter if I was in meters or not, because they're going to cancel anyhow. So 40, enter 0.190 times 30 divided by, so I get 253 grams. I'm going to go to 2 sig figs because I was using the 10 gram increment weights. So we say 250 grams. And if we measure this guy on the balance, the real balance, and it was 260 grams. So that's actually pretty good. Well, let's see how good that is. We'll check out the percent difference. Oops, I'm just making up symbols here. So the percent difference is going to be 260 grams minus 250 grams over 260 grams times 100%, and we get 260, enter 250 minus 260 divided by, so I get, not bad, I get like 3.8% error. So pretty good considering we knocked that out in about 2 minutes, and good fun. So you guys will be doing activities similar to that. So this is kind of the main crux of the calculation is to balance the torques. The torque goes like the distance R, the force, the side of the angle, and you put those in equations, bada bing. You notice I switched to grams here from kilograms. That's okay. Have a good day and be careful out there. Cut.